Hello and welcome to this Revision Monkey video on what's going to be in the separate Physics Paper 2 exam. This video is for the AQA specification and separate science pupils, otherwise known as triple scientists, who study more content and do the 1 hour and 45-minute papers. As you are all probably aware, you do not need to recall the physics equations. So this is what your physics equation sheet will look like. So it has all of the physics equations on there for you. You will need to use the physics datasheet with the equations on to write down certain equations. For example, this says write down the equation that links force, mass and acceleration. So you'd look for the words force, mass and acceleration on the datasheet and write down the correct equation. So just having a quick overview of calculations. If you get a 2 marker, that would mean to substitute the numbers into the equation. So for a question such as calculate the force needed to accelerate a 10 kilogram ball at 2 meters per second squared, if you're given the mass and acceleration, you would write down the equation, put the numbers that you're given into the equation, and then work out your answer on a calculator. If you see 3 marks, that will involve something else, such as rearranging the equation or including your units, or perhaps converting a number first of all if you see nano, micro, milli, kilo, mega or giga in front of it, or something like significant figures. Occasionally for a 2 marker you might have to rearrange as well, but normally they give you an extra mark for that, so look out for that in a 3 mark question. There is much more information on this in the Physics Paper 1 video, so if you didn't watch that, do go and look over it, because 30% of your exam is equations. But I'll assume you've watched that, and this is just a quick overview. If you move on to 4 mark questions, then you might expect any 2 of those things, like rearranging the equation, remembering the units, conversion, or significant figures. Then for 5 or 6 marks, there's your clue to use 2 equations and any of the above. So think that if you can't use 1 equation to get your complete answer, you might have to use 1 equation, then some more information in the question, and a second equation to get to the final answer. And as well as that, expect rearranging units, conversions and significant figures as well. So the units that you need to be aware of for Physics Paper 2 are on the screen. You might want to pause the video and think if you can remember all of the units for those quantities. Well done if you remembered that force is newtons, capital N. Weight is also newtons, because weight is a force. Mass is kilograms. As a reminder that that's the only time you leave the kilo prefix there. Okay, mass comes in kilograms, so you don't have to convert that quantity. Extension or distance is meters. Energy is joules. Pressure, pascals. Area, meters squared. Velocity, meters per second. Acceleration, meters per second squared. Wavelength in meters. Frequency in hertz. Wave speed in meters per second. And magnetic flux density in teslas. Now I've left out a few units because these are ones that can be calculated by using the equations. The first one is gravitational field strength. If you use the equation weight equals mass times gravity and rearrange that to make gravitational field strength equals weight divided by mass, there you get your units, because newtons divided by kilograms will then be the units for gravitational field strength. Force equals spring constant multiplied by extension in meters. Rearrange that for spring constant equals force divided by extension, and you end up with the units for spring constant being newtons per meter, because you've done force in newtons divided by meters. The momentum unit, well, momentum is equal to mass in kilograms times velocity in meters per second, so you just put those 2 units together and end up with kilogram meters per second. Another one is the unit for moment, where moment equals force times distance, because you've got the unit for force and distance being multiplied together, then the unit for moment is Newton meters. The required practicals for this paper are the acceleration practical, using the equation F equals ma, and the trolley. The springs practical, investigating Hooke's law. The waves practical, looking at waves in a ripple tank as well as waves on a string. the infrared radiation practical involving the Leslie's cube, and the separate only practical which is on reflection and refraction.
Investigating springs required practical. In this practical, you're going to see how the force applied to a spring affects the extension of a spring. First of all, you need to secure a clamp stand to the table using a G-clamp. This is because you're going to put lots of weights on the bottom of the spring and you don't want it to topple over. You then attach a clamp to the clamp stand and hang a spring from the clamp, like so, and attach a meter ruler to another clamp stand and measure the original length of the spring. Then attach a 1 Newton mass to the bottom of the spring and record the new length of the spring. Calculate the extension of the spring by subtracting the original length from the length after 1 Newton was applied. So our extension is going to be the difference between the original length and the new length. So this here is going to be our extension. We then add another Newton weight to the spring, so you have 2 Newtons in total now as the force being applied to the spring. And we measure the new length of the spring and again calculate the extension by subtracting the original length of the spring. We then repeat it for the following weight. So we keep adding weights to the bottom and we'd use 3 Newtons, 4 Newtons and 5 Newtons, for example, on the bottom of our spring. So each time we are changing the force, and this is going to be our independent variable, and we are calculating the extension, which is our dependent variable. And for our control variable, we need to make sure we're using the same spring each time because it must have the same stiffness. So with our results of force and extension, we should then plot force against extension on a graph. And you will see a relationship that looks a little bit like this. Any straight line relationship that goes through zero is a directly proportional relationship. So force applied is directly proportional to extension. So looking at the graph in more detail, this links to an equation which says that force equals spring constant times extension, F equals KE. So if you wanted to calculate spring constant from your values, you would rearrange that equation so that you would have K equals F divided by E. And if you do that, you can see that by calculating the gradient of the graph, so by drawing on a triangle and calculating the change in y divided by the change in x, essentially you're doing force divided by extension so you can calculate the spring constant. That is why it's important to have force on your y-axis and extension on your x-axis. Otherwise, you'd have to do 1 divided by the gradient to get your spring constant if you had the axes the other way around. So if you plotted it with extension against force, you'd have to do 1 divided by the gradient to actually get your spring constant. So it's better to do it this way around. Hooke's law then states that for an elastic object, extension is directly proportional to force. And what it means by an elastic object is an object that will return to its original shape after being stretched. So through all of the forces that are applied here, the spring is obeying Hooke's law because force is directly proportional to extension. However, if you keep applying more force, eventually you will reach the limit of proportionality. And this is the point whereby the spring no longer obeys Hooke's law and it is the point where it stops being directly proportional. And you can see the graph curves off here. So at this point you've added too much force on the bottom of the spring and it is now inelastic. It won't return to its original shape. So your spring will just be overstretched like so with all the masses on the bottom, and if you remove the masses, it won't return to its original shape. Investigating acceleration required practical. So for this practical, we're going to need the equation that links force, mass and acceleration, and that's our F equals ma equation. Force in newtons equals mass in kilograms multiplied by acceleration in meters per second squared. So in essence, for this practical, if we're investigating acceleration, this is what we need to measure. This is going to be our dependent variable. And we could either investigate how force affects acceleration and make this our independent variable, or we can investigate how mass affects acceleration and make the mass our independent variable. So I'll talk you through both practicals now. First of all, let's discuss how we are going to measure acceleration, because that is our dependent variable. So remembering the equation for acceleration will help with your understanding with this part. The acceleration equation is acceleration equals the change in speed over time. So we've got a final velocity, an initial velocity, divided by time to give us our acceleration. In this practical, to measure acceleration, we are going to use a light gate. And our light gate is attached to a data logger, which is then attached to a computer. So it can record the acceleration for us automatically. In our practical, we have an object like a trolley which is pulled along by a piece of string. Now, in order to measure the acceleration of the object, we must have this shaped card on top of our object. So the reason why it has to be this shaped is because you need two pieces of card going through the light gate so it can measure initial velocity with the first piece of card that goes through and final velocity and then calculate acceleration. So what we need to do is we need to measure the width of these two pieces of card and put that information into our data logger so it knows the width of card that's travelling through the light gate. That will then automatically calculate the speed of the card going through, and it will do the difference in the speed or velocity over time to give us a calculation of acceleration, and all of that will be done automatically. We are going to discuss how to set up the full practical in just a minute, but to calculate the acceleration part of it, we're using string to pull the trolley through the light gate, which will automatically record acceleration for us. The diagram below shows the rest of the equipment that we need to set up for the practical. Here's the light gate that we just said previously is going to measure our acceleration. We've got a trolley or a moving object with our specially shaped piece of card on top that is going to go through the light gate and measure our acceleration. To pull the trolley along, we've got a piece of string which goes round a pulley, and it has a hook with some masses on the end. Now this part of the system is just a group of objects, so we'll call the whole thing a system. This part of the system is applying the force. So we said previously we could either change the force and investigate how force affects acceleration, or we could change the mass. Now if we want to change the force applied to the trolley, we need to change this part of the system here, because these masses here are applying a downwards force which is accelerating the trolley. So for force, we would change this part of the system. If we wanted to change the mass of the system, we would be changing the mass of the trolley over here on this section. So shortly I'm going to go through two practicals, one whereby you change the mass and keep the force the same, and one whereby you change the force and keep the mass the same. But each of them you're measuring acceleration using the light gate. Now you'll notice I've put the trolley here on an air track. You might not have that in the exam, they might just be talking about it on a table. However, the air track is really good because it reduces friction. So if they don't use an air track, you could talk about this as an improvement to the method. So let's first look at the practical whereby we change the mass of the system but keep the force constant. In this practical, we are going to keep the weight on the hook, the force which we're applying over here. We're going to keep that constant, so we're not going to change anything about this part of the system. We'll place the trolley at the start of the air track, and we must make sure we've got the same starting position each time. So this is going to be a control variable, the same starting position. We then let go of the trolley and measure the acceleration using the light gate, and that will give us our first reading. Because we need to change this part of the system if we want to investigate how mass affects acceleration, this is where we're going to change the mass of the trolley. So you can see here I've added one mass to the back, and then we're going to repeat the process. So return the trolley to the start position and add a 100 gram mass to the trolley. Release the trolley and measure acceleration using the light gate. So we then repeat this using the following masses on the trolley, so 200 grams, and then 300 grams, and then 400 grams, and we'd use 500 grams as well. And we then repeat the experiment 3 times and calculate a mean acceleration for each mass. So that's our practical when we want to see how mass affects acceleration and when we use mass as our independent variable. Now we'll look at how force affects acceleration. So for this practical, we're going to change the force which we apply to the system, but this one's slightly different because we need to keep the mass of the whole system the same. Every time we change this, we have to place a mass over here, and the reason for that is to keep the mass of the whole system the same so that we're not actually changing mass, so we're keeping mass constant. A little bit of a difficult concept to understand, but in the exam they'll expect you to write about moving the masses from here to here. So we keep the mass of the system constant, and this time change the force, so the weight acting on the pulley. So we'll start with no masses on the trolley and 5 newtons on the hook attached to the string. Now it doesn't have to be 5 newtons, that's just a random example that I've given. You may well be using much smaller masses and therefore using a much smaller force to pull this down, but let's just say we're starting with 5 newtons on the string. We're then going to release the trolley from the starting position and calculate the acceleration using the light gate. And then to change the force applied, remove a mass from the hook down here and place it on the trolley. And that's because I said, as before, because the total mass of the system must remain constant. So you can see here I've removed one of the masses from down here and placed it onto the trolley instead. And then we do exactly the same thing, let the trolley go from the starting position and measure acceleration using the light gate. We'd repeat by moving another mass from the hook and placing it on the trolley so that the force is now 3 newtons that we're pulling down with, and again measuring acceleration. And then we'd repeat it for the following forces, so perhaps 2 newtons, moving them up here, and then we'd do it again with 1 newton as well. We'd repeat 3 times for each force applied and calculate a mean acceleration for each force. So in your exam, look very carefully to see whether they want you to change force or whether they want you to change mass, because the practicals are slightly different, but both of them you're measuring acceleration using the light gate. Investigating wave properties required practical. In this practical, we're going to use the equation V equals F lambda. So the V stands for wave speed, F for frequency, and wavelength. Now, a lot of the times you'll be asked to calculate wave speed, and to do so you will need to know the frequency and the wavelength of the wave. But you may well have a situation where you have to rearrange this equation to perhaps calculate frequency or wavelength instead. So there's 2 practicals that you might need to do to measure wave speed, and the first one that we'll look at is waves on a string. For this practical, we set up a piece of string on a vibration transducer and pull it tight using masses and a pulley. So you can see the wave forming here, but before we turn on the signal generator, you will just have a tight piece of string like that, which is being kept tight by the masses here, which are providing a downwards force. Now the signal generator is connected to the vibration transducer, and when you turn that on, this will vibrate up and down, so it will oscillate vertically up and down and will produce a wave, like so. We need to turn on the signal generator and set the frequency so you can see a wave clearly. So if it's oscillating up and down at a frequency where you can't see a clear wave, you're going to have to tune it on the signal generator until you see a nice clear wave forming. We then measure the wavelength using a ruler. It is more accurate to measure several wavelengths, then divide by the number of wavelengths you have measured. So this would show one complete wavelength where it goes up, down and back again to the same position. That would be one wavelength. So you could well get a ruler and just measure one wavelength like so. But to increase the accuracy, you could measure a bigger distance and divide by the number of wavelengths there are. So for example, we could measure the complete distance from here to here using a ruler and work out how many wavelengths that is. So we've got 1, 2, 3 and a half wavelengths. So if we divide them by 3.5 wavelengths, that will give us a much more accurate measurement of one wavelength. We then use the equation V equals F lambda to calculate wave speed. So wave speed equals the frequency, which you get from the signal generator because you've set that yourself. So let's say, for example, it could be 20 hertz. And then you would multiply that by the length of one wave to calculate wave speed. Another way in which you can calculate wave speed is using a ripple tank. So you'd set up a ripple tank with a shallow tray of water. Adjust the signal generator to a frequency that shows clear waves in the water. The dipper, which is just here, will then oscillate at the set frequency and create waves. So the dipper will move up and down vertically in the water, creating waves in the water. We need to adjust the frequency of the strobe light here until a clear pattern of wavefronts is seen on the screen. So you'll have a screen or a piece of paper underneath whereby you're going to see the shadows created by the wavefronts. And if we imagine a water wave, which is a transverse wave going like that, the wavefronts you're seeing are the peaks of the waves like so. And to measure wavelength, we can simply measure the distance between two of those wavefronts, and that will give us one wavelength. But again, like the previous example, it would be more accurate if we measured a bigger distance and divided by the number of wavelengths we had. So we'd use a ruler, measure the lengths of say 10 waves. I don't have 10 on the screen, but in your exam they'll probably give you one with many more wavelengths than this. And then we divide by 10 to get the length of one wavelength. Again, we use the equation V equals F lambda to calculate wave speed, and we're getting our frequency from the signal generator that we've set at a very particular frequency, which incidentally will be the same as the strobe light, because to get a clear pattern on the screen they have to match in frequency. And then the wavelength we're going to get by measuring several wavefronts and then dividing by the number of wavelengths that we've got. Infrared radiation required practical. There's 2 practicals that we could look at for infrared radiation. The first one is to do with emitting infrared radiation, and the second one is to do with absorbing infrared radiation. So in this first practical, we'd place a Leslie's cube on a heat-proof mat and fill it with boiling water from the kettle. Now the Leslie's cube is just a metal cube with different coloured surfaces on the vertical sides. So for example, you could have a white surface like this, you could have a matte black surface, a shiny black surface, and a silver surface, for example. Using a ruler, we would measure a set distance, so I've just suggested 15 centimetres, from one side of the Leslie's cube and place an infrared thermometer here facing the cube. We'd repeat for the other three faces, making sure that the thermometer is always 15 centimetres away from the cube. This will detect the amount of infrared radiation that is emitted by each side of the Leslie's cube. You would then repeat the experiment 3 times and calculate a mean for each side. The surfaces, such as matte black, which are really good emitters of infrared radiation, should give you really high readings of infrared radiation coming off of the Leslie's cube, whereas surfaces such as white and silver, which are poor emitters, will have lower readings. Alternatively, you could be asked about the absorption of infrared radiation instead of emission. And in this practical, you would stick something metal, like a coin, to different surfaces, for example black paper and white paper, using wax. You would then put the surfaces equal distance from a Bunsen burner, so you'd measure with a ruler to make sure that they were exactly the same distance away, and this would be our control variable, the distance between the Bunsen burner and the material. And you would time how long it takes for the coins to fall. And then you'd repeat the experiment 3 times and calculate a mean. So the materials that are better at absorbing infrared radiation, like matte black, it is not only a good emitter of radiation, but if you are a good emitter, you are also a good absorber. So this material should absorb the infrared radiation that's coming from the Bunsen burner a lot quicker, causing the wax to melt and the coin to drop quicker than, for example, a white surface. Reflection and refraction of light, required practical for separate scientists only. First of all, we'll remind ourselves of the 2 different types of reflection that we can have. If you have a rough surface, like this one shown on the left here, then the rays of light coming in will all hit different angles of surface. They will all obey the law of reflection, whereby the angle of incidence is equal to the angle of reflection. However, the light will be scattered because each ray of light will be reflected off at different angles. So this one's called diffuse reflection, and this image over here shows specular reflection, which happens on a smooth surface, whereby again all of the rays of light obey the law of reflection, but they're all being reflected at the same angle. And this is called specular reflection, and this will give us a really clear reflection. So you may be asked to investigate how different surfaces reflect light. You would choose a variety of objects that you want to reflect the light, for example a mirror, paper, foil and glass. You draw a line on a piece of paper, like shown, and place the object on the line. So you'd position a ray box directed at the object and shine a single beam of light, like so, onto the object. Using a pencil, draw the incident, which is the ray going in, and the reflected rays on the paper. So you might have something that looks a little bit like this. Draw a normal line. This is the normal line, which is always at 90 degrees to the surface, and measure the angle of incidence, so that's this angle here, which is between the normal and the incident ray, and the angle of reflection. You would then repeat this for the other objects, and also record the width and the brightness of the reflected ray. Because if you've got specular reflection, you're going to get a really thin and bright reflected ray coming out. However, if you have more diffuse reflection, you would have a wider ray of light coming out, and it would be dimmer as well, or perhaps you wouldn't see a reflected ray at all on some materials. For this practical, you'd want to keep the angle of incidence the same, so keep the ray box in a fixed position, and also keep the power of the lamp in the ray box the same. They would be important control variables. The thing that we'd be changing is the object that we are reflecting from, and the thing that we are going to be measuring, well, there'll be several things. We'll be measuring the angle of reflection, but we might also be recording the width of the ray and the brightness of the ray as well. So there may be several things we're recording in this experiment. In the exam, they may well also ask you to actually keep the object the same and instead change the angle of incidence and measure different angles of reflection. So they might manipulate this practical slightly and ask you to investigate something slightly different. But that's the basic setup that you need to follow. We looked at reflection before. This time we are going to look at refraction, which is the bending of light as it goes through a different medium. We will select a range of transparent rectangular blocks made of different materials, for example different plastics and different types of glass, for example. We then position a ray box so that it shines a single beam of light at an angle to the rectangular block. So this is our incident ray going in here. Using a pencil, we then draw around the block And using a pencil and ruler, we draw the incident ray, which is this one here, and the emergent ray that comes out of the block. So our diagram might look something like this to start off with. The outline of the block with the incident ray and the emergent ray that comes out of the block. We then remove the block and draw a line to connect the incident ray and the emergent ray, which is shown in this diagram here. Just like we did in our reflection diagrams, we need to draw a normal line at 90 degrees to the surface where the incident ray meets the block. So this is the incident ray going in. And we need to measure the angle of incidence, which is between the incident ray and the normal line, and the angle of refraction. So this is the refracted ray going through, so this is our angle of refraction. We then repeat this for the different material blocks and repeat it 3 times for each block and calculate a mean angle of refraction. So for this practical, our independent variable is going to be the different material blocks that we're using. Our dependent variable is the angle of refraction. And for this practical, we're going to want to keep our angle of incidence the same. So this is going to be a control variable.
Let's first look at the difference between scalar and vector quantities. Some examples of scalar quantities are speed, distance, and time. And some examples of vector quantities are velocity, displacement, force, acceleration, and momentum. Now, the difference between the two is that scalar quantities have magnitude only. So magnitude is size. So you can give one of these quantities a big value or a small value, and that will be changing their size. So for example, a speed of somebody could be 5 meters per second. That's giving the size of the speed or the magnitude. Somebody could walk a distance of 10 meters, for example, and that's the size that you give it. Whereas a vector quantity has both magnitude, so the size, and direction. Velocity is the vector quantity which is related to speed. So you'd give, rather than just giving a size like 5 meters per second, you'd also give some indication of direction. So you could say to the right, or in physics sometimes you'll see that they'll put a plus or a minus in front of the velocity as they've given a plus or minus to a certain direction. So if they've decided that everything moving to the right is a plus and everything moving to the left is a minus, they can put that plus or minus in front to indicate the velocity. Displacement is the vector version of distance, and you'll also have force, acceleration, and momentum that are examples of vectors as well. A little something for higher tier then. Motion in a circle involves constant speed but changing velocity. This is just checking your understanding that speed is scalar and velocity is a vector. So something is travelling at constant speed but changing velocity. Now that must be because it's changing direction. So they'd have the same magnitude all the way around. For example, this ball travelling around in the circle, let's say it was travelling at 10 meters per second, round and around and around and around. Well, yes, it'll have a constant speed as it's travelling around, but because it's constantly changing direction as it's going around the circle, then its velocity is changing. Not the number on the velocity, but just the direction. So it'll always be 10 meters per second, but the velocity will be changing because it's a changing direction and velocity is a vector. So moving on to forces then, we said it's a vector, so we can use arrows to show both the size of the force and the direction of the force as well. So for example, with this falling tennis ball, it will have air resistance going upwards, represented by this arrow, and weight acting downwards, represented by this arrow. The direction of the arrow shows the direction of the force, and the size of the arrow shows the magnitude of the force. So we can group forces into contact and non-contact forces. So some contact forces include friction, air resistance, tension, and the normal contact force. And in these cases, all the objects have to be touching. So friction is when two objects are rubbed together. Air resistance, you've got the air particles colliding into an object. Tension, you'll experience that when you pull two different ends of material like a rope. And a normal contact force is a contact which is acting at the normal, which is at 90 degrees to the object, which is touching another object. So for example, a book on a table would experience a normal contact force at 90 degrees from the table. Some non-contact forces include gravitational force, electrostatic force, and magnetic force. And in all these cases, the objects are separated and don't have to be touching in order to experience the force. Some forces can be measured using a Newton meter, and and forces are measured in newtons. So this is a Newton meter. You could, for example, hang your object on the end of this hook here, and that will let you know the weight of the object in newtons, or you could use this Newton meter to pull or push an object and measure forces in that way. Let's have a look at this example. We've got a diver diving off the diving board, and we've got a gravitational force pulling that diver down towards Earth, or we can actually call this weight, because weight is equal to mass multiplied by gravitational field strength. Weight is a force, and it's measured therefore in newtons. Mass is measured in kilograms, so if you ever see it in grams, you would have to convert it to kilograms by dividing by 1,000. And gravitational field strength is measured in newtons per kilogram. The weight acts at a single point known as the centre of mass of an object. So here, for example, in this person, this could be the centre of mass of that person. It's quite difficult to work out for irregular shaped objects where the centre of mass is, but that's where the weight will be acting downwards. On Earth, the gravitational field strength is 9.8 newtons per kilogram, sometimes round up to 10. What is the weight of the diver if he has a mass of 50 kilograms? Well, weight is mass times gravitational field strength. So if we do the mass times by 9.8, we'll get a weight of 490 newtons. Let's look at an example if this diver was on the moon. On the moon, the gravitational field strength is just 1.6 newtons per kilogram. What is the weight of the diver if he has a mass of 50 kilograms? Well, importantly, the mass does not change. Mass is still 50 kilograms, but if we multiply it by 1.6, the diver would have a weight much less of just 80 newtons. So the key thing is your mass, wherever you are, does not change. However, your weight, because in physics weight is a force, we're not talking about mass in kilograms. When we're talking about weight in physics, we're talking about a force in newtons. So really it's important to say that your mass, you're talking about your mass when you step onto some scales, rather than your weight, because in physics weight is the force with which you're pulled towards an object. So that's why on the moon your steps will be a lot lighter and a lot bouncier, because there's less of a gravitational field strength pulling you towards the moon compared to the Earth. So important, mass stays the same wherever you are, but your weight can change depending on the gravitational field strength of the planet you are on. Looking at resultant force, then you can think of the resultant force as the overall force acting on an object. So when you take into account lots of different forces, what's the overall force? So if we look at this block here, we have 5 newtons pulling to the right and 2 newtons pulling to the left. So the 2 newtons pulling to the left, we need to take away from the 5 newtons on the right, and we would have an overall force of 3 newtons. And because a force is a vector, we'd have to tell the examiner the direction that that box will move in as well. Because there's more newtons pulling it to the right, overall it would be pulled to the right. You might also get an example where there's multiple forces acting on an object. For example, if it's still 5 newtons pulling to the right, but in this case we've got 2 newtons and 3 newtons to the left. Overall on this side there'll be 5 newtons pulling it to the left and 5 newtons to the right. So 5 minus 5 would be 0 newtons. So when there's 0 newtons, there is no resultant force, or it's better to say no overall force, and the resultant force is 0. There's a little bit extra for higher tier students where you might be asked to complete a free body diagram, which is a diagram which represents an object and the forces acting on that object. So this question says complete the free body diagram to represent a ball with a resultant force of 10 newtons downwards. Well, at the moment it's got 5 newtons up, so if we want a resultant force of 10 newtons down, then we must have 15 newtons acting downwards, because overall now we'd have 15 minus 5, giving a resultant force of 10 newtons downwards. And this could well be a scale diagram where you'd have to really accurately draw the arrow in an exam. The second question says complete the free body diagram to represent a ball with a resultant force of 0. So this is just checking your understanding. If there's 5 newtons upwards, to get a resultant force of 0, there must be a 5 newtons force downwards. A little bit more tricky work on forces for higher tier students is resolving forces. This question says resolve the force into its horizontal and vertical component. And what this is saying is if this force is acting at an angle, we can break up that force into the horizontal component of that force and the vertical component of that force. So this is an example of what you might need to do. You would draw the force on a graph paper that they would give you in the exam. So draw the arrow to the correct size and scale. They might even put this one on there for you already drawn if you don't have to copy it from a diagram down there. You'd have this arrow and you would need to measure this arrow to calculate your scale. So if we measured it and it was, for example, 8 centimetres, we could look at our scale. So we'd have 5 newtons for every 8 centimetres. And if we divide both sides by 8, that will make this 1 centimetre, because 8 divided by 8 is 1, and that will make this 0.625 newtons. So now you've got your scale, you know that every 1 centimetre equates to 0.625 newtons. You can then draw an accurate horizontal line along the bottom, measure the length of this line, for example 7.5 centimetres, and use the scale to calculate the force. So we multiply each centimetre by 0.625. So 7.5 times 0.625 would give you a force of 4.69 newtons. And vertically, we again would draw a straight line to the top of this force, measure it with a ruler, and then use our scale to calculate the vertical force. So that's taking a force at an angle, resolving the forces into the vertical and horizontal components of that force. And what this is basically saying is, yes, we've got this force at an angle, and this would be like pulling this object here with an upwards force of 1.75 and a sideways force of 4.69 newtons, and that would result in the object moving in this direction with a force of 5 newtons. You could also have a scenario where they ask you to calculate the resultant force when these forces are at angles, so it's not as straightforward as writing a force going to the right and a force going to the left. What you'd need to do is you need to redraw the force arrows, but draw them end to end this time. So if we start off with this one, and at the end of this one we are going to draw the next arrow like so. This gap here is going to give us the size and the direction of the resultant force. So you'd measure it from this point, because this is where we started, up, and you would draw an arrow connecting to that second force that you've put on. So just neaten that up here for you. This arrow here would represent the resultant force, and try and be really accurate, more accurate than I have, to make sure your arrow starts here and meets at the tip of that arrow. You could then be asked to work out the direction of that resultant force. So if we put this vertical line here, you could measure the angle relating to 0 and 180 down here. You could measure that angle using a protractor. That's why you're asked to bring a protractor in the exam. And you could be asked to measure that, for example. So that could be around 40-ish degrees, but you'd need to do it accurately. And you could also be asked to use a scale diagram to calculate the size of that force. So they'd have to give you some values here in order to measure the scale diagram. For example, if they told you that was 5 newtons, you can measure that line in centimetres and work out what each centimetre would be worth in newtons, and then calculate the size of that force. A fine example is if you see a situation where the forces are in equilibrium. When forces are in equilibrium, there is no resultant force. So again, you draw the arrows end to end in any order. So let's look at one scenario. You could draw this one here first, and then on the end of it, this one here, and then on the end of it, this one here. And what you'll notice is they form a complete shape without any gaps. And in that case, that's telling you that the object is in equilibrium and there is no resultant force. Doesn't matter what order we put these arrows in. We could start with the longest one first, and then this one, and then this one. If they complete that complete shape with no gaps, then there is no resultant force, and the object is in equilibrium. So we'd say the resultant force, in this case, is 0. In this topic, we need to distinguish between scalar and vector quantities, and the two we're going to focus on are speed and velocity. So the scalar quantity speed has magnitude only, which means it only comes with a size, whereas velocity is classed as a vector because velocity tells you both the size and direction of movement. So for example, with speed, if an object was moving to the right at 3 meters per second, we would just class the speed of the object as 3 meters per second. However, with velocity, we need to indicate the direction that the object is moving in. So what they do in physics is they state which direction is positive and which direction is negative. So, for example, a scientist could say, right, let's say that everything moving right is positive and everything moving left is negative. So rather than just writing 3 meters per second, if an object was moving to the right, when we talk about velocity, we'd have to be talking about plus 3 meters per second. So this here just indicates the direction that the object's moving in, hence taking into account direction as well as size. If the object was moving in the opposite direction, then at that same speed, we would then be saying it would be minus 3 meters per second to show it's moving in the opposite direction. So they are both very similar things. They're to do with how quickly an object moves. However, speed just takes into account the size, whereas velocity takes into account direction as well. And then there's another pairing to look at, which are distance and displacement. Displacement is the vector version of distance. Let's have a look at an example. If we have a starting point and an object moves 5 meters and then another 5 meters, the total distance would be 10 meters, 5 plus 5 making 10. However, if we look at the same scenario with displacement, with an object moving 5 meters and moving another 5 meters, because it's returning back to the same original starting point, we would actually say that there was a displacement of 0 meters because they've gone up and come back to this same starting position. So therefore, its displacement is 0. So that's the difference between the scalar and vector quantities, speed versus velocity, and distance versus displacement. You need to learn some typical speeds off by heart, so I suggest writing these down, having them on some revision cards to learn them. And these are walking, 1.5 meters per second, running, 3 meters per second, cycling, 6 meters per second. So if you remember walking, running, cycling, each time these are doubling up. These are typical speeds. And then you also need to know for some other modes of transport, which is a car, 25 meters per second, a train, 30 meters per second, and an aeroplane, 250 meters per second. So when they talk about a scenario, for example, a car travelling, and they want you to do some mathematics with that, they might ask you to estimate something about the motion of that car. And if they do, and they haven't given you a speed, then you should be using this typical speed for a car. And the same if they talk about an instant involving, for example, the momentum of a cyclist, and they're talking about estimating momentum. Well, think that the typical speed of cycling is 6 meters per second. So these are just some facts to remember. A couple of other little facts then. Firstly, that the speed of sound is 330 meters per second. And also they just want you to have an understanding that the speed of wind varies. Okay, so sometimes it might be really fast wind, sometimes it would be really slow wind, as you probably know, but that's just one thing that they might ask you to apply your understanding of in the exam. Let's look at some speed equations then. This question says a bee flies at a speed of 10 meters per second for 40 seconds. How far does it travel? So this is applying the equation distance travelled equals speed times time. Distance travelled is measured in meters, speed is measured in meters per second, and time is measured in seconds. So for us to calculate this, we would do 10 times 40, which would give us 400 meters. With distance time graphs, you need to be very careful that the y-axis says distance and not velocity, and it'll always be over time. So a straight line at an angle, like this one here, shows that an object is moving at constant speed. A straight line that is horizontal shows that the object is stationary, and here again we would have another constant speed. This line here is much steeper than the third line over here, so it shows that it's moving at a faster speed. It's travelling more distance in a certain amount of time. And this one here, a lot shallower gradient, which means it is travelling at a slower speed. You can calculate average speed on a motion graph using the following equation. Speed equals distance over time, which is just rearranging that distance travelled equals speed times time equation. If you want to calculate the average speed in the first 10 seconds, you draw a line from 10 up to your graph and then across and read off your distance that it had travelled in 10 seconds. So we know here that within that first 10 seconds it's travelled 40 metres. So if we do 40 divided by 10, we'll get a speed of 4 metres per second. A curved line that gets steeper shows that an object is accelerating. And a curved line that gets shallower shows that an object is decelerating. If you're doing higher tier, you'll have to calculate the speed at a particular point on a distance time graph. For example, you might be asked to calculate the speed at 10 seconds. And in this case, you'd have to draw a tangent on the graph at 10 seconds. So here is our 10 seconds going up here, and that's why we've drawn a tangent at this point, which is a straight line as close to the graph as you can get it. You would then calculate the gradient of the tangent by doing the change in y divided by the change in x. So draw a triangle anywhere on that tangent, and we can calculate the x value, the y value, and we remember we always do the y divided by the x. So we do 17 divided by 7.5 to give us 2.3 metres per second. Velocity time graphs. With velocity time graphs, you need to check that the y-axis says velocity and not distance, because that's a different motion graph. With velocity time graphs, a straight line at an angle would show a constant acceleration. A flat line here would show a constant velocity because it's not moving above 40 metres per second in this case. A straight line going downwards at an angle would show constant deceleration. And then here we've got another straight line at a different velocity, so that again shows another constant velocity. You can calculate acceleration on a velocity time graph by calculating the gradient. So essentially we're using the equation acceleration is the change in velocity over time, where v is the final velocity and u is the initial velocity. You'll remember that one because u comes before v in the alphabet, so u is the starting one and v is the final one because that comes after. So if, for example, we said what is the acceleration in the first 10 seconds, we would calculate the gradient of this line here. So we'd have a look and we'd see that we have a velocity change from 0 to 40 in that 10 seconds. So 40, take away 0, so that's your final minus your initial divided by 10, which is your time, should give us the acceleration. So acceleration in this case would be 4 metres per second squared, and have a look at the units for acceleration there. For higher tier, you'll also have to calculate the acceleration at a particular point. So if we have a look at this graph here, where the acceleration is changing because it's a curved line rather than a straight line. If, for example, we were to ask for the acceleration at 10 seconds, we would draw a tangent at 10 seconds, determine our values for y and x from that tangent, and do the change in y divided by the change in x. So if we had a look at this, for example, we'd have 17 divided by 7.5 to calculate an acceleration of 2.3 metres per second squared. For high tier, you might actually have to calculate the distance travelled on a velocity time graph, and to do this you calculate the area under a graph, because essentially you're using the equation distance travelled equals velocity multiplied by time. And if, for example, we're asked to calculate the distance travelled in the first 10 seconds, this would be the area of the graph we are looking at, but we need to calculate the area just under the graph, this shaded region here. So if we take some values from this graph, we're going to calculate the area. So if we do the area of the rectangle and then divide it by 2 to get the area of the triangle, that will be our easiest thing to do. So in the first 10 seconds, the velocity is 40 metres per goes up to 40 metres per second. So if we do 40 times 10, which is equal to 400, and then we'll divide that by 2 because we've got ourselves a triangle, our distance travelled will be 200 metres. If we were calculating the distance travelled between 10 and 25 seconds, that would be this region here. You wouldn't need to divide by 2 because you're not looking at a triangle, you're looking at a rectangular section. So let's consider the motion of this skydiver who's just jumped out of a plane. All objects falling towards the Earth will be accelerating at 9.8 metres per second squared. So this skydiver will have the force of weight accelerating him towards the Earth. And as he initially jumps out of the plane, he'll also have a very small air resistance acting in the opposite direction, which is shown by a smaller arrow. So here we've got a scenario where weight is larger than air resistance, and therefore the motion will be acceleration, so he's accelerating towards the Earth. And then as speed increases, so as he accelerates, then air resistance will also increase until you get to a point where the air resistance will balance out the weight, shown by the same size arrows here, and in this case he will be not accelerating anymore, but he would have reached a constant speed. And when he's falling, because he's falling through a fluid, we call this constant speed a terminal velocity. So fluids are liquids and airs, and air, if you are falling through a liquid or a gas like air, then you are said to reach a terminal velocity, which is your final velocity. You can't go any faster than that at the point that your weight matches the air resistance, is balanced by the air resistance. So then the parachutist will deploy a parachute, and at this point there is a much larger air resistance and a smaller weight, which will cause a deceleration. And then finally, the air resistance and the weight will balance each other out again because he'll slow down and air resistance will decrease. So those two will balance out again, and he will reach a new constant speed, and therefore, because he's falling, a new terminal velocity. So for separate science, you'll also need to link this into a velocity time graph, so looking at how the shape of the graph explains the motion. So if we look at the skydiver again, at this first point we could be sketching acceleration until he reaches his first terminal velocity. So here at this point he had unbalanced forces and was accelerating, and then at this point he reached balanced forces and was reaching a terminal velocity here of 60 meters per second. Then after his parachute opens at this point here, he would have a large deceleration until he reached his final velocity, again another terminal velocity here, because the forces become balanced again. So relating the force diagrams to motion graphs will be something that you might have to do. Forces, accelerations, and Newton's laws of motion. Let's have a look at Newton's first law. This is all to do with the resultant forces acting on an object. And the first part of it says that if the resultant force acting on an object is 0, and the object is stationary, then it remains stationary. So for this vehicle here, you've got the weight acting downwards, a normal contact force acting upwards. There's no air resistance or thrust here, so these two forces are balanced. The object is stationary, and there's no resultant force, which means it's just going to stay stationary. In the second example, if the resultant force acting on an object is 0 and the object is moving, the object continues to move at the same speed and in the same direction. So the object continues to move at the same velocity. So because velocity takes into account speed and direction, if the resultant force of this car is 0, because here we've got your normal contact force, your weight, and the thrust and the air resistance are balanced out, this car is moving, and it has no resultant force, then the object will continue to move at the same velocity. So have a look very carefully to see whether the object is already stationary or whether it's already moving. Because if it's stationary and there's no resultant force, it will stay stationary. If the object's moving and there's no resultant force, it will just continue to move at the same velocity. The velocity of an object, so taking into account the size of the speed or the direction of the object, will only change if there is a resultant force acting on the object. So let's say we increased this thrust here, so we had a greater forward force compared to our air resistance. Now we have unbalanced forces. We will have a resultant force overall acting in this direction here because of this increased thrust. And then now we'll be changing velocity. We'll be changing the speed, not necessarily the direction, but the speed of the object as it will accelerate forwards. Newton's second law says the acceleration of an object is proportional to the resultant force acting on an object and inversely proportional to the mass of an object. This links to the equation F equals ma, or force equals mass times acceleration. Force is measured in newtons, mass in kilograms, and acceleration in meters per second square. So look out for this symbol here. This shows that acceleration is proportional to the force, and you might also see it in a sketch graph of acceleration against force as well. So for example, if we had force and acceleration, they would be directly proportional. And this means as force increases, acceleration increases. And in the other relationship, acceleration is inversely proportional to mass. And this means as mass increases, acceleration decreases. So inverse proportion means as one thing gets bigger, the other thing gets smaller. And that's where you'll see a graph, if we put mass against acceleration, would look a little bit like this. As mass increases, acceleration decreases. Let's have a look at an example. A boy kicked a 500-gram stationary ball with a force of 20 newtons. Calculate the acceleration of the ball. Well, first of all, let's look at converting the grams into kilograms. So 500 divided by 1,000 would give you 0.5 kilograms. So do look out for those kind of things in the exam. The equation we're using is force equals mass times acceleration. That's one that links to Newton's second law. And we'll put the numbers in that we've got. So 20 newtons is the force, 0.5 kilograms is the mass. So if we rearrange this, acceleration would be equal to 20 divided by 0.5, which will give us an acceleration of 40 meters per second squared. For height here, you also need to be aware of the meaning of inertia, and that is the tendency of objects to continue in their state of rest or of uniform motion. So if objects are already stationary, they'll in the state of inertia, they'll remain stationary, or if they're already moving, they'll continue moving in a uniform motion. So looking at our F equals ma equation, if we rearrange F equals ma, we get mass equals force divided by acceleration. And this type of mass, within this equation, once you've worked out force divided by acceleration to calculate your mass, when you've calculated mass this way, this is called inertial mass. And it is a measure of how difficult it is to change the velocity of an object. So acceleration is changing velocity, force, the force you need to change that velocity. So that, when you calculate mass, is called inertial mass. And it is defined as the ratio of force over acceleration. So that's shown in this F equals ma equation. Inertial mass is calculated by force divided by acceleration. So actually, scientists haven't found that this inertial mass is any different in terms of size to any other way you'll calculate mass, but theoretically, this particular mass here that you calculate by doing force divided by acceleration has got this special name of inertial mass. Newton's third law says that whenever two objects interact, they have to be two different objects. Whenever two different objects interact, the forces they exert on each other are equal and opposite. So this is that equal and opposite law. So for example, when you sit this mug on a table, the mug will exert a force on the table, and the table will exert a force on the mug that is equal in size and opposite in direction. When you press this button here, one object is the finger, the other object is the button. The finger will press the button with a force and apply a force to the button, and the button will apply a force in the opposite direction that is equal in size and, as I said, opposite in direction. Forces and braking. Let's first of all look at stopping distance, which is made up of thinking distance, which is the distance the vehicle travelled during the driver's reaction time. So this could be a definition that you're asked to write. Don't forget it's got the word distance there. So thinking distance is not to do with time, but it's the distance travelled during the driver's reaction time. And braking distance is the distance the vehicle travelled under the braking force. So these are definitions people get wrong a lot of the time because they start to think about time rather than distance. So if we add these two together, thinking distance plus braking distance, we will get the overall stopping distance. So driver's reaction time normally falls within typical values of 0.2 and 0.9 seconds, but this can be varied by different things that we'll discuss later. So let's have a look at a scenario here. We've got a car driving along and a woman steps out. So the point then here that the driver notices the woman in the road will be the point that he starts to think about putting on the brakes. And at this point later on, this is the point where he actually applies the brakes, then this distance in between will be the thinking distance, the distance the car travels during the driver's reaction time. Because he sees the woman, but don't forget the car is still travelling, but by the time his brain has told his foot to apply the brakes, then the car would have still travelled a certain distance, which is that thinking distance. He then applies the brakes, and then the braking distance is the distance under the braking force, so it is the distance travelled between this point that he applies the brakes and this point when the vehicle finally comes to a stop. And the total distance is therefore the stopping distance, the thinking distance plus the braking distance. And importantly, if we add these up, 10 metres plus 20 metres, for example, we can calculate the overall stopping distance for the car. Thinking distance and braking distance both increase with speed. So both of these sections here are going to get longer the faster you are going. And therefore stopping distance in total increases with speed, hence why you have lower speed limits in areas where there are more pedestrians. Certain things can affect thinking distance, including tiredness, that will increase the thinking distance. Drugs, most drugs will increase the thinking distance because they'll slower your responses. Some of them may increase it if it's a stimulant as well. Some of them may decrease the thinking distance if it was a stimulant that improved your reaction time. Alcohol, that is a depressant, so that would increase the thinking distance. It would take longer for you to react to apply the brakes, and distractions as well. So all of these things can affect thinking distance, most in a negative way, which will increase the distance. And then braking distance, that's things that would affect the distance travelled under braking. So those are wet or icy roads. It would take longer to stop, therefore the braking distance would increase. The condition of the tyres, there's not enough tread on the tyres, that would affect the ability of the car to stop, and the braking distance would be longer. Condition of the brakes, again, if there's not a good thickness on those brake pads, then that will affect the ability of the car to stop. When you brake, work is done by friction between the brake and the wheel, and that's because you will apply a force against the wheel to slow the car down. So you're doing work because work done is equal to force times distance. So if you apply force over a certain distance, you are doing work. And if you remember, work done is the same as energy transferred. So when we're doing work, we are also transferring energy. And in terms of a car slowing down, the kinetic energy of the vehicle decreases and the temperature of the brakes increases. So you've got a decrease in the kinetic energy store of the vehicle and an increase in the thermal energy store of the brakes. And really large decelerations may lead to the brakes overheating and a loss of control. So you can see here bright orange glowing wheels here because the temperature of the brakes has increased so much. And the greater the speed that you are travelling, the larger the braking force that is needed to stop the car within a certain distance. So the faster you're travelling, the bigger the braking force you need to stop the car, and therefore the more likely you are to have these overheating brakes and a loss of control as well at those greater speeds. Reaction time varies, but is usually between around 0.2 and 0.9 seconds. I'm not going to dwell on this practical because you would have done it in detail in Biology Paper 2 as a required practical, but you can use the ruler drop method to measure reaction time. So person A would drop a ruler, and then person B catches the ruler as soon as possible, and we can use a conversion chart to convert the distance that the ruler fell through the hand, this part here, into a reaction time. But if you want lots more detail on that, you can look back over the required practical that comes up in biology. Let's have a look at some acceleration equations then. We've got A equals v minus u over t, where acceleration is in meters per second squared, final velocity in meters per second, initial velocity in meters per second, and time in seconds. So you should remember that u becomes before v in the alphabet. So u is your initial or starting velocity, because that comes first, and v is your final velocity, because that comes afterwards. Let's have a look at this question. A dog was sat still when he heard someone at the gate. The dog reached the gate in 2 seconds, so that is going to be our time, and was travelling at 6 meters per second when he reached the gate. So this is our final velocity. Calculate the acceleration of the dog. Calculate A. So the other bit we need is u. We need the initial velocity, so you need to read the question very carefully again. It says a dog was sat still. So this here implies that the dog was stationary, therefore that is our starting velocity, which was 0. So then we can do 6 minus 0, so v minus u, divided by the time, which is 2, and our acceleration would be 3 meters per second squared. Then we've got another acceleration equation, which is v squared minus u squared equals 2as. Again, acceleration, final velocity, initial velocity. S in this equation is distance. And let's have a look at this practice question. It says an aeroplane accelerated at 10 meters per second squared from 100 meters per second to 200 meters per second. Calculate the distance travelled by the plane while accelerating. So this time we're rearranging this equation to calculate S. You might have to rearrange the calculation to calculate any one of U, V, or A. So let's have a look at it then. 200 squared is our final velocity here. U is our initial velocity of 100 meters per second. So we square that, and then that is equal to 2, which is our constant in our equation, multiplied by acceleration of 10, multiplied by s. So if we simplify this, we're saying that 30,000 equals 20 times s, because those two make 30,000, those two make 20, and then rearranging it to 30,000 divided by 20 equals s. So s is equal to 15,000 meters. Momentum. Momentum is equal to mass times velocity. Momentum is measured in kilogram meters per second, which is the unit for mass multiplied by the unit for velocity. So you just write the two next to each other. Mass is measured in kilograms and velocity is measured in meters per second. The conservation of momentum says that the total momentum before an event is equal to the total momentum after the event. Now let's look through some worked examples for momentum calculations. The first one that we'll do is a collision. In this question, it says stone 1 slides to the right and hits the stationary stone. After the collision, it kept moving in the same direction at 0.5 meters per second. Calculate the speed with which stone 2 moved to the right. So initially, the speed of this stone 1 was 2 meters per second and its mass is 20 kilograms. That was moving to the right and it hits this stationary stone, stone 2, that is stationary. So this tells us that it has a speed of 0 meters per second and it also has a mass of 20 kilograms. So the momentum of stone 1 before is 20 multiplied by 2 because mass times velocity is momentum. So the momentum before of stone 1 is 40 kilogram meters per second. And the momentum before of stone 2 is 20 times 0, which is 0 kilograms meters per second. So if we add those two together, the total momentum before would be 40 plus 0, which is 40 kilogram meters per second. So all we've done is before the collision, we've worked out the momentum of stone 1, that was 40, the momentum of stone 2, that was 0. Add them together and we get the total momentum of the whole system before the collision. So the total momentum after, because of conservation of momentum, must also equal 40 kilograms meters per second. That's not given to us. That's just through our knowledge of the conservation of momentum, that total momentum before is equal to total momentum after. So now we can calculate the momentum of stone 1 after, because in the question it told us that it kept moving in the same direction, but this time at 0.5 meters per second. It's got the same mass, so it's still a 20 kilogram stone. So this time its momentum is 0.5 times 20. So now its momentum is 10 kilograms meters per second. So that's momentum of stone 1. So if we know the momentum afterwards should be equal to 40, we know that 10 kilograms meters per second of that is taken up by stone 1. So we know that momentum of stone 2 must be 30 kilogram meters per second, because 40 minus 10 is equal to 30 kilogram meters per second. So stone 2, we can calculate the speed or velocity with which it moves to the right, because momentum equals mass times velocity rearranged will give us momentum divided by mass equals velocity. So if we take the momentum of 30 divided by the mass of the stone, which is also 20, this tells us that stone 2 moved away with a velocity of 1.5 meters per second. Now let's look at an explosion example. This one says a cannonball with a mass of 5 kilograms is fired from a 100 kilogram cannon at a speed of 150 meters per second. And the question says calculate the velocity of the cannon as it recoils in the opposite direction. So when the cannonball is fired out, that will go in this direction, and the cannon itself will recoil in the reverse direction. So we've got the total momentum before is 0 kilogram meters per second. And that is because before the explosion, everything is stationary. The cannon is stationary and the cannonball inside is stationary. So nice easy one, we know the momentum before is going to be 0. That means the momentum afterwards must also equal 0 because the momentum is conserved. So we can work out the momentum of the ball from the information in the question, because we have been told it has a mass of 5 kilograms and it travels with the speed of 150 meters per second. So mass times velocity is equal to 750 kilograms meters per second. And you'll notice the plus here, because we're talking about velocities. I have decided that going right is a plus direction, and going in the opposite direction will assign that a minus. So the ball is moving to the right, so we're going to describe it as plus 750 kilograms meters per second, and the recoil of the cannon will be a minus number. So the momentum of the cannon afterwards is, we know, must be minus 750. And we know that because total momentum afterwards must be equal to 0 because of the conservation of momentum. And if the ball has gone forward plus 750 kilogram meters per second, then to get to 0, the momentum of the cannon afterwards must be minus 750, because if you add those two together, you get a total momentum afterwards of 0 kilogram meters per second. Okay, so that's how you get to that bit. So we know the momentum of the cannon afterwards is minus 750 kilogram meters per second, and if we rearrange momentum equation, momentum divided by mass is the velocity. In the question, they've told us the mass of the cannon is 100 kilograms, so if we rearrange that, we will get minus 750 divided by 100 to give us a velocity of minus 7.5 meters per second. And again, the minus is there just because velocity is a vector, so it shows us, or gives us an indication of the direction that that cannon is moving in. Work done and energy transfer. When a force causes an object to move through a distance, work is done on the object. So because we're talking about distances, we can say a force does work on an object when the force causes a displacement of the object, because distance and displacement are linked. Distance is scalar and displacement is vector. So there's an equation that links work done, force and distance, and this is work done equals force times distance, where work done is measured in joules, force is measured in newtons, and distance is measured in meters. The reason why work done is measured in joules is because it's the same as energy transferred, and obviously energy is measured in joules. But you do also need to be aware of another unit for work done, and that is Newton meters. So 1 Newton meter is equal to 1 joule. And the Newton meter comes from the fact that you're multiplying a force measured in newtons by a distance measured in meters. So you might see work done in Newton meters, or you might see it in joules. So an example using the calculation calculates the work done when 20 newtons of force pushes a wooden block 25 centimetres. So the first thing we need to do is sort out these units, because we said distance needs to be in metres. So convert this to metres first of all. 25 centimetres is equal to 0.25 metres. And then put our numbers in the calculation. Work done equals the force multiplied by the distance, which would equal to 5 joules. Or, like we said in the exam, you might see it as 5 Newton meters. Forces and elasticity. To squash or stretch a stationary object, you need to apply to forces that push or pull an object. So the other word for squash is to compress. So you need 2 forces, because otherwise if you just had one force applying against the object, that would cause the object to accelerate in the direction of force, because of force equals mass times acceleration. So if you just had one force, that object would accelerate in the direction of the force. However, if you have 2 forces, that can then, in this case that we're going to do, cause the object to compress, or equally, if they were pulling, you could cause the object to stretch. To stretch a spring, you need to apply 2 forces that pull either end of the spring. So, for example, you could have it on a clamp here, and you could add some weights to that, so you'd have the force of weight acting downwards, and then a tension force acting in the opposite direction. That is 2 forces, therefore applying on the string and allowing it to stretch. So there are 2 types of objects. There are elastic objects. Those are objects that return to their original shape after being stretched. So if you think of a spring, once you remove a weight, as long as it's not too much of a force that has stretched it, if you let go of that weight, take it off, it will return to its original shape. And in that form, it is elastic, and we could say it has been elastically deformed. So when you take off the forces that are being applied to that spring, it will return to its original shape. Inelastic is the opposite. So inelastic objects are the opposite to elastic objects. They don't return to their original shape after being stretched. So again, we would say an object in this case has been inelastically deformed, and there's no chance of getting that to return to its original shape. Hooke's law: some elastic objects, importantly, obey, like springs, obey Hooke's law. Hooke's law states that when you double the force applied to an object, the extension of the object also doubles. And there's an equation that comes into play here, which is force is equal to spring constant times extension. Force is measured in newtons, spring constant is measured in newtons per metre, and extension is measured in metres. So force is directly proportional to extension in elastic objects. So if we were to plot force against extension, this time I've got it in centimetres, but you could also have converted it to metres. When an object is obeying Hooke's law, a graph of force against extension will show a straight line that goes through zero. Remember, this relationship is called directly proportional. Any straight line through zero is directly proportional. If the object is overstretched, it will lose its elastic properties and the graph curves off. And this point here, we'd call its elastic limit, or limit of proportionality, because that is the point that it is not proportional anymore. So here is its limit of proportionality. And at this point, it's gone beyond its elastic limit and no longer obeys Hooke's law. Work is done when a force stretches or compresses an object. And in this case, remember we're talking about two forces needing to stretch or compress objects. And energy is transferred to the elastic potential energy store of the object. So we know that work done and energy are both measured in joules, because work done is the same as energy transferred. So when you compress or stretch an elastic object, it will transfer energy to the elastic potential energy store. And this equation links our factors. We have elastic potential energy is equal to 0.5, which is a constant, that stays the same, multiplied by spring constant, multiplied by extension squared. And we measure elastic potential energy in joules, spring constant in newtons per metre, and extension in metres. All waves transfer energy. There are two types of waves, longitudinal and transverse. A sound wave is an example of a longitudinal wave. In a longitudinal wave, there are regions of compression and rarefaction. So here we have all the particles close together, and that's a region of compression. And next to it, where the particles are further apart, that's a region of rarefaction. In a longitudinal wave, the oscillations are parallel to the direction of energy transfer, which means the movement of the particles backwards and forwards is parallel to the direction of energy transfer. Water and light are examples of transverse waves. In a transverse wave, the oscillations are perpendicular, which means at 90 degrees, to the direction of energy transfer. So that means whilst the particles oscillate up and down, the direction of energy transfer is perpendicular. An oscilloscope can be used to view wave properties. So you've got the peak and the trough. A represents a wavelength and B represents the amplitude of the wave. So one complete wave is where you start from one point, go down and up again to the same point. So that could be one complete wave, or starting here, going up, down and up again to the same point would also be one complete wave. So you could also measure the wavelength between these 2 points, for example. That would also be wavelength, that would be same distance as you've measured over here in A. Frequency is the number of complete waves that go past a certain point per second. Frequency is measured in hertz. So wave B on the diagram has a higher frequency than wave A, because more waves are passing a certain point every second. There is an equation that links to frequency, which is period equals 1 divided by frequency, and period is the time it takes for one complete wave to pass a certain point. So there's one complete wave, and period would be the time it takes for one wave to pass a certain point. So you might get a question like, calculate the time period of a wave with a frequency of 20 Hertz, and you'd use the equation, put the numbers in, and then your answer would be in seconds, because period is the time it takes for one complete wave to pass. The speed of sound in air is approximately 330 meters per second. So we can use the following equipment to measure the speed of sound. We've got a signal generator connected to a speaker, and we can set the signal generator to a particular frequency, for example 200 Hertz, and that means the speaker will oscillate backwards and forwards 200 times a second. Then, if we place two microphones equal distances from the speaker and connect these to an oscilloscope, we will get two different wave fronts on the oscilloscope. We'll get one for microphone 1 and another for microphone 2, and they will be identical because they are equal distances to the speaker. Then you would move one of the microphones, let's say microphone 2 for example, you would move that backwards, and as you do that the wave front will move as well, and then it won't be identical anymore. So you'll have microphone 1 here with your complete wave, and microphone 2 would have shifted slightly to the right as you'd moved the microphone backwards. But then, if you move microphone 2 back a little bit more, you'll eventually get to the point where you have identical wave fronts again. And as you can see here, both of these traces are in exactly the same positions again. And when you do that, you can work out the wavelength of the sound wave generated by the speaker, because that is the distance between the two microphones. And you would measure that with a ruler and record that distance, for example 1.65. So now we have a frequency, which is 200, set by the signal generator, and a wavelength of 1.65, which we've measured as the distance between the two microphones when the wave fronts realign perfectly. We can then use the wave equation V equals F lambda, or wave speed equals frequency times wavelength, to calculate the speed of sound. So in this case 200 Hertz as set by the signal generator multiplied by the wavelength of 1.65 gives us 330 meters per second.
Electromagnetic waves. Electromagnetic waves are transverse, and they all travel at the same speed, which is 3 times 10 to the 8 meters per second. You need to know the order of electromagnetic waves in the spectrum. So this is showing the order from the longest wavelength to the shortest wavelength, and the order will be radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. And this is also the order from the lowest frequency wave to the highest frequency wave. So down this end of the spectrum, you'd get the longest wavelength waves, and at this end of the spectrum, the shortest wavelength, high frequency, high energy waves. Don't be put off in the exam if they ask you to list them in the other way, from shortest wavelength to longest, from gamma through to radio waves. In the middle, the visible light is split up into red, orange, yellow, green, blue, indigo, and violet. So if you were to split what we call white light, you would see this spectrum of colours. So you need to know that order, Roy, G, Biv. And you'll see that the red is closest to the infrared light in the spectrum, and the violet is closest to the ultraviolet. And this is why lots of things emitting ultraviolet will also emit parts of the visible light spectrum, and you'll see them as violet. Things that emit infrared radiation will also often emit part of the visible light of the spectrum, so they will come through to your eyes as red. Our eyes detect only visible light. So there are lots of other waves of electromagnetic radiation, but our eyes, as an organ, only detect visible light. Some animals, for example, can see into ultraviolet light, but our eyes only see visible light. The high frequency, short wavelength, high energy end of the spectrum can have hazard effects on human body tissue. So these are UV, X-rays and gamma rays. For example, ultraviolet light can prematurely age the skin and cause skin cancer. And it's important in the exam, if you're talking about ultraviolet, that you must link this directly to skin cancer and not just generally write cancer. X-rays and gamma rays are both ionizing. That means they can strip electrons off of atoms. So they can cause gene mutations and also cancer. And we could be a bit more general there because they can cause different forms of cancer. So these ones are particularly dangerous, and ultraviolet we should try and avoid as much as possible as well through sun creams and wearing appropriate clothing in the sunshine. Radiation dose is measured in a unit called sieverts, and it's a measure of the risk of harm resulting from radiation exposure. And it's useful in hospitals because there will be doctors and nurses and other staff members that work in areas where there are, for example, lots of X-rays or gamma rays. Or patients might need to have lots of X-rays or treatment involving gamma rays. And you need to know how the radiation dose is going to affect you and what the risk of harm is. So radiation dose takes into account two things. It takes into account the type of radiation that you're exposed to and the size of the dose that you get. Okay, so you need to bear in mind that radiation dose takes into account the type and the size of radiation that you are exposed to, but you don't have to remember that the units are sieverts. So you might see sieverts in a question when they're talking about dose, but you don't have to remember those units. So let's look at the uses of some of these electromagnetic waves. Radio waves are used for TV and radio communications. Microwaves are used for satellite communications or for cooking food. And because it's a spectrum, it will be a different wavelength used for cooking food compared to the wavelength that you would use to communicate with satellites. Infrared radiation, that's used in electrical heaters, cooking food. So both of these two will obviously glow red because it's close to the red part of the visible light spectrum as well. And also infrared cameras, which will detect infrared light rather than visible light. So the heat or infrared coming off of objects will be detected by those cameras. Visible light used for fibre optic communications. Ultraviolet light used for things such as tanning beds or energy efficient lamps using ultraviolet. X-rays, medical imaging, and gamma rays, medical treatment. So gamma rays are often used to kill cancer cells, for example. For higher T, you need to know a little bit more about how radio waves are transmitted. So for TV and radio communications, radio waves can be produced from alternating current. So be able to watch the TV or listen to the radio when it is communicated via radio waves. You have a transmitter and a receiver. The transmitter will produce a radio wave. Okay, so alternating current, which I've abbreviated to AC here. So alternating current in the transmitter produces a radio wave, and that receiver absorbs the radio wave, and then this generates its own alternating current, which is at the same frequency as the radio wave. So frequency, remember, is measured in hertz. So whatever the frequency of the radio wave is, that will produce an alternating current of the same frequency inside the receiver. All electromagnetic waves change direction when they enter a different medium. So you can think of this as a different material. So this is called refraction. So refraction is when waves change direction when they enter a different medium. So here you've got the medium of air, and here's your barrier, and the other side you've got glass. So air and then glass. So this wave is coming in here, hitting the glass, and is bending. So rather than carrying on this same direction that it was going through first of all, it's bending and changing direction to head out this way. And if it enters a denser medium, it will bend towards the normal, which is in the case of this diagram here. So air is less dense than glass, so the wave is heading in this direction. It's going from the less dense air to the more dense glass, so it bends towards the normal. The normal is this imaginary line here, this dotted line. This is the normal line, and this is drawn at 90 degrees to the surface. So here at the boundary that it joins here, this angle here is 90 degrees, and that is the normal line, or you could draw the 90-degree angle there, either or. It is 90 degrees to the surface. So rather than carrying straight on here, you can see this is bending towards the normal, so this angle will be a lot larger than this angle here. A little bit more refraction for height here. Refraction occurs as the wave slows down, so you might be asked to explain why refraction happens, okay, because it slows down as it enters the denser medium. If it was going at the same speed, it would travel straight on like so, but because it slows down, it bends towards the normal in this direction. You also need to complete the diagram to show the waves moving from a less dense to a more dense medium, but you might have to show this as wave fronts, which are shown here. So these are wave fronts, and what you can imagine these are, if I draw a wave for you now, like so, if we were to look at the top of the wave and look at these peaks, these would be the wave fronts moving through the water. So it would look a little bit like this for this wave here. So if you measure the distance between the wave fronts, you're getting the wavelength because it's the distance between two peaks. So as this wave is entering the more dense medium, shown by this grey area over here, they will change direction. So if we draw a normal line onto this diagram here at 90 degrees to this change in medium line here, the waves will bend towards the normal. So at the moment they're coming in this direction. Rather than going straight on, they're going to bend towards the normal like so, and therefore if we draw the wave fronts to the other side, we'll draw them continuing here along the bottom and then show them changing direction. So here we've got our new wave fronts in a different direction, and also what you'll see is the wave fronts are closer together because the waves are slowing down. Here's another example. This time you'll notice here is the boundary between the less dense and the more dense medium. This is the more dense, this is the less dense. So here's the boundary, but this time you can see the waves are actually travelling at 90 degrees to the boundary, so they're travelling along the normal, and therefore if they were to continue through that boundary to the side, they wouldn't change direction because they're travelling along the normal. However, they would still slow down, so you would still need to draw your wave fronts closer together, but they don't need a change of direction if they travel along the normal. Permanent and induced magnetism, magnetic forces and fields. Let's first of all look at permanent magnets. So permanent magnets have a north pole and a south pole, and opposite poles attract each other, so north and south here will attract, and like poles repel each other. So if you bring two south poles together, those will both repel, and if you bring north poles together, they will also repel. Magnetic elements are iron, cobalt and nickel. So there are only 3 magnetic elements. Other substances can be magnetic. For example, steel is an alloy that is magnetic, but that's because steel contains iron, and iron is a magnetic element. So you will see other substances that are magnetic, but that's because they will include one of these magnetic elements. Let's look at induced magnets. So if we were to bring 2 paper clips together, they would not attract each other and it would fall down again. However, because paper clips, most of them are made out of a magnetic material, a lot of them are made with iron in them, then if we were to place this inside a magnetic field of a permanent bar magnet, so here's our bar magnet, if we bring our paperclip close to that, so it is within its magnetic field, then it will become temporarily magnetic, and it will then be able to attract the paperclip. So we would call this now an induced magnet. So an induced magnet becomes magnetic when it's placed in a magnetic field. An induced magnet quickly loses its magnetism when removed from a magnetic field. So after a little while, the attraction here would go away because that paperclip wouldn't be magnetic anymore and it would simply fall away again. We can draw magnetic field lines around a permanent bar magnet. So there are invisible magnetic field lines to show the magnetic field. Magnetic field lines always point from north to south. So you can see here we've got north, so these field lines coming out here have the arrows to show they're going away from north, and the field lines on this end show they're going in towards south. And at the top here, the lines are going from north to south, shown by these arrowheads, but at the bottom, look carefully, they're also pointing left because they're going from north to south. So you'll need to be able to draw these magnetic field lines around a bar magnet like this, and draw the arrows on as well. You just draw at least 2 lines above, at least 2 lines below, and a few coming out of the poles. So the closer the field lines, the stronger the magnetic field. So at the poles here, where the lines are closest together, that will be where the magnetic field is strongest, and you'll get your strongest attraction here. Looking at compasses, because they involve magnetism as well, the Earth itself has a magnetic field, and actually at the North Pole, that is where there is magnetic south, and at the South Pole, that's where there is magnetic north. A compass contains a small bar magnet, and this bar magnet here is on a frictionless surface, so it can turn all the way around freely. And a compass, the north part of the compass, will point towards magnetic south. Okay, it is the North Pole, hence why we can direct ourselves around the globe using north and south. But the actual small bar magnet inside here is pointing towards magnetic south, because if you remember, in magnets, north is attracted to south. So the Earth's invisible magnetic field has a magnetic south at our North Pole. So if we put the plotting compasses around, you can see at this North Pole here, you've got the north part of the magnet being repelled and facing away, so that's going in this direction, out from the north. And at the South Pole, the north is attracted to the south, so that's going in towards the south. And then around the outside, you've got these plotting compasses here and here. So this one, again, is always going from north to south, so you can see here, going from north pole of the bar magnet towards the south, so the north part is being repelled towards away from this north and attracted towards the south. And again at the top here, this plotting compass here, the north part, this small bar magnet inside the compass, is being repelled by the north pole of the permanent bar magnet and being attracted towards the south. So you'll see here the field lines will then look very similar to our normal bar magnet when the field lines are away from the north and into the south pole. The motor effect. When a current flows through a conducting wire, a magnetic field is produced around the wire. So let's have a look at the right-hand thumb rule. You can use your thumb to show the direction of current, and for example, if your thumb is pointing upwards, the direction of current will be up from positive to negative, and your fingers will show the direction of the magnetic field. So you can imagine your fingers pointing inwards like so, and importantly, it has to be your right hand that you use to do this. So if you make a fist and a thumb with your right hand, the thumb would show the direction of current, so in this case we could do positive to negative, and your fingers would show the direction of the field lines. If the current is flowing in the other direction from positive to negative, you simply turn your thumb upside down and that will show you the direction of the field lines depending on where your fingers curl into your palm. So if we use that rule on this wire, you've got the wire travelling up here from positive to negative, the current would be upwards, so we could point our thumb up like shown in the diagram here, and the magnetic field lines would curl round into our palm like so. So we can draw the arrows on the field line going in that direction. The magnetic field line is stronger closest to the wire, and you can see that because the field lines are closer together, so they're stronger closer to the wire, and as they get out they would just get further apart and weaker. And if you increase the current flowing through the wire, the strength of the magnetic field also increases. A coil of wire is called a solenoid, so this would be a solenoid, and a solenoid, if it has a current flowing through it, will produce a magnetic field. So very similar to the bar magnet, you've got your north and your south, and the field lines always go from north to south. The magnetic field line inside a solenoid is strong and uniform. You can see that by these straight lines of the field lines inside. They're really close together, so the magnetic field is strong and uniform because there are straight lines of field lines going through. If you add an iron core, you increase the strength of the magnetic field, so if you put a core inside there, and a solenoid with an iron core is called an electromagnet. So if you were to put an iron core inside that coil, we could now call that an electromagnet. Electromagnets are useful because when an electromagnet is switched off, it loses its magnetism. So if we switch these off now, it would drop the nails, and this makes it useful for picking up objects and dropping them somewhere else. So for example, on a scrapyard, they're used to pick up magnetic objects and drop them somewhere else in the scrapyard. A little bit on the motor effect for higher tier. When a conductor carrying a current is placed inside a magnetic field, the magnet producing the magnetic field and the conductor exert a force on each other. This is called the motor effect. So if this wire here was carrying a current, if we were to place this inside the magnetic field of this bar magnet, the magnet and the wire would both exert a force on each other, because don't forget, this wire, because it's carrying current, will also be producing its own magnetic field, and that's why they produce a force on each other. So we can use Fleming's left-hand rule to work out the direction of motion that a wire would experience if placed in a magnetic field. So when you do the Fleming's left-hand rule, you must use your left hand, which is different to the right-hand grip rule that we looked at earlier. Your thumb, your first finger and your second finger must all be placed at right angles to each other. And your first finger you should put in the direction of the magnetic field, which will always be from north to south. If you set that one up first, it's a little easier. Your second finger will then go in the direction of current, which always goes from positive to negative. And if you set these two up, then automatically your thumb will be pointing in the direction of the motion, which is going to tell you which way the wire moves. So for example, it might move up or down, or maybe left or right, depending on which system you are looking at. So if we look at this example, this is a simple motor. You've got some magnets here, a north and a south of two magnets, and you have a wire going in between. So these magnets are producing a magnetic field. You're placing a wire carrying a current in the magnetic field from positive to negative, so that will experience a force. So the first finger, you point north to south, so you'd point the first finger in this direction. You would point your second finger in the direction of current, so that will be from positive to negative. And when you do that, automatically your thumb should now be pointing downwards, and that will tell you that the wire moves down. If it's not pointing downwards, you may be using the wrong hand. You've got to use the left hand for Fleming's left-hand rule. So when you have a coil of wire carrying a current in a magnetic field, it will rotate. And this is the basis of an electric motor. So if we apply Fleming's left-hand rule to each side of the coil, you can see which side goes up and which side goes down. So when I say each side, have a look at this side of the wire and have a look at this side of the wire, and you work out which one goes up and which one goes down. In both cases, the direction of the magnetic field is going to be from north to south. But on this side of the wire, because you've got positive going to negative, so the current goes along here, all the way down, round, and over here. Because we've got that direction, on this wire, the direction of the current is like so, and on this wire, the direction of the current is in the opposite direction. So if you apply Fleming's left-hand rule to that, you will see that this side will be going up and this side will be going down. And this will tell you if the motor spins clockwise or anti-clockwise. So in this case, if this side of the motor goes up, this side goes down, then we must have a clockwise motion on the motor. However, we want a motor to keep on spinning, and if we just did this, we would end up with this side being over here and that side being on the opposite side, and it would just stop. But we need it to keep spinning and spinning and spinning, and this is where this part of the motor becomes important. This is a split ring commutator, this part here, and this switches the direction of the current every half turn so that the coil of wire keeps spinning. So we said that this one would go up, this one would go down, and there would be a clockwise motion. However, that would just stop if it wasn't for the split ring commutator. This switches the direction of current, so then this side will go down, this side will go up, and it will just keep on spinning round and around and around, which provides the basis of our electric motor. Extra equation for higher tier is force is equal to magnetic flux density multiplied by current multiplied by the length of wire. So the force that the wire experiences is equal to essentially the strength of the magnetic field multiplied by the current flowing through the wire multiplied by the length of the wire that is inside that magnetic field. So FBIL is for short. So force is measured in newtons, magnetic flux density is the B part, and that's measured in Teslas, capital T. Current I is measured in amps, and length L is measured in meters. So a quick example might be something like calculate the force on a 20 centimetre wire with a 3 amp current flowing through it in a magnetic field with a magnetic flux density of 0.4 Teslas. So using FBIL, we first convert our 20 centimetres into meters, and then we put our numbers in. Force is equal to 0.4 Tesla times 3 amps times 0.2 meters, which would be equal to 0.24 newtons.
Rest of the topic then, forces. So moments and levers. What are they all about? They're force multipliers that basically let you increase a force without actually having to use a bigger force. And how they do that is you increase the distance between where you're applying the force and where the force is needed. So what I mean is the moment, the turning effect of a force is equal to the force I'm applying times by the perpendicular distance from the pivot. Perpendicular distance means, so here is my force being applied to this spanner here. Perpendicular distance means the distance from 90 degrees from that force up to the center of my pivot. So that is my distance there. On this spanner, that wouldn't matter too much. It'd be fairly easy to take that measurement. But on different situations, it might be harder for you to take that measurement. So really important is at 90 degrees to where the force is. So here we have our effort, okay, and our perpendicular distance would be at 90 degrees to that effort. So that there is our distance D. And similarly here, if our effort is that direction and here is our pivot, we're going to want to find the distance between the pivot and the force. Now, if we want an object to balance, what we're going to need to know is that the clockwise moment equals the anti-clockwise moment. So basically, on a seesaw, our turning effect that way is equal to our turning effect that way. Now, we might possibly see it with multiple objects on a seesaw. So I've got, let's say, an object here and an object here, and they balance with an object over here. Okay, I just have to work out the moment of this object and that object and add them together. And those two moments added together should equal the moment over on this side. Okay, so gears now. Gears is a really small topic, but well worth knowing how they increase force. So gears are just discs with teeth around the edge, and they transmit a turning force from one place to the other. You've got them on a bicycle. They can also be used to increase the moment of a force or reduce the moment of a force. Now, if this is my driver gear and this is the next one along, so I'm turning the driver gear and it's attached to a larger wheel, if I increase the size of the gear, it increases the moment. And the reason being for that is that I'm now further, my force is now being applied further from the pivot. And of course, the further you are from the pivot, the stronger the turning force. Excuse me. So if I reduce the size of the wheel, I'm now reducing the distance from the pivot. So I'm reducing the size of the force. Okay, fluid pressure. So as I go deeper under the sea, pressure increases with depth. And why does it do that? Well, it increases because the number of particles above them increase, and the weight of all those particles increases the force pushing down. So we might see with this tall column of water, if I was to make holes all the way down, we'd see that the deeper the hole, the higher the pressure, so the further that water shoots out the bottom there. Now, static fluid pressure does not depend on the shape, the total mass, or the surface area of the liquid. And we've seen a GCSE question where you have sort of three weird shaped containers all connected together, and it showed you the level of water in one of them, and it wanted you to show the level of water in them all. The level of the water will be exactly the same because the pressure will be exactly the same because the pressure isn't dependent on the shape of the container. So this is a separate science equation. So pressure at any point underneath the water is found by the density of that water times by the strength of gravity times by the height underneath that water. So it is literally only interested in the water that's above it, that's in height, and we need to know the density of that water and the strength of gravity. Now, atmospheric pressure, similar kind of science here. At higher altitudes, air pressure is less. The higher the altitude, the fewer particles there are above, pressing down with a smaller force. So if we look at our guy stood on top of the mountain here, it's lower pressure because there's fewer atoms pressing down on him. And down at the bottom here, more pressure because there's more particles above, the weight of all of those particles pushing down on him. And here we go, we've got a graph showing a relationship between altitude and pressure. And we can see that the pressure is really low up high and increases with as you get closer to the ground. Upthrust. Why do things float? So this apple is displacing water. As it's in the water there, it's pushing some water out of the way. Now the size of the upthrust force, so there is a force from the water on the apple upwards, the size of that force of the weight of the water it's displaced. So remembering that weight is a force, so the volume of water there, the weight of that volume of water will be the same size as the upthrust force. So we can say that that piece of water there will have the same weight as the upthrust. How can we explain this upthrust force? Well, why does a cube of ice float upwards when in water? So this is to do with fluid pressure again. And pressure increases with depth because of the weight of the particles pressing down from above. So here's my ice cube. Because pressure increases with depth, that means that there's going to be a higher pressure, therefore a higher force at the bottom. And you can see these force arrows tell us that there is a higher force upwards due to the higher pressure than there is at the top, downwards. So the base of an object feels a higher water pressure than the top, meaning a resultant force upwards. And this is called upthrust. The upthrust is equal to the weight of the water displaced. Okay, the rate of change of momentum. So crumple zones in a car, airbags, seatbelts, gym crash mats, cycle helmets, playground surfaces, what have they all got in common? They're all safety features which reduce the forces on a person. It's forces on a person that causes them injury. High forces are bad, low forces are good. So they do this by reducing the rate of change of momentum. In other words, they make going from a high momentum, because don't forget that momentum is mass times velocity, they make going from a high momentum to a low momentum, they make that occur over a longer period of time. So whenever you crash, you're going to have a high speed down to hopefully 0, but you want that to occur over a long period of time. So let's see how we do that. How can we prove that to reduce forces on a person in a crash, we need to increase the time they stop over? Well, F equals ma tells us that in order to reduce this force here, if I want the force to go down, I can't change the mass of myself in an accident, but I can reduce the deceleration. So I can make that number go down. How do I make the acceleration go down? Well, acceleration is change in speed over time. If I'm in a crash, I can't change my starting speed and my final speed. It's going to be fast to stopped. But I can change my time taken to stop. If I change my time taken to stop, I change my acceleration. My acceleration will go down. So we can combine these two things together. So let's have a look at this. F equals ma is my equation. I swap a for v minus u over t to make this equation here. Force equals mass times the change in speed over the time taken. So this is the rate of change of momentum, because there is my momentum equation, and it's how quickly does that momentum change. Okay, waves topic. So in the waves topic, you need to know just a little bit more in depth about each of the individual waves. And so for long radio waves, it's used for long distance communication. The reason why it can be used for transmitting around the Earth is it can bend or diffract around the surface of the Earth. Medium wave radio can reflect off of the ionosphere. So it's reasonably high quality and it can bounce off the atmosphere. Shortwave radio, again, high quality communications. That's really clear, crisp broadcasts, again, can reflect off the ionosphere. TV and radio, okay, now they can only work in direct line of sight. And microwaves for satellites, well, why are they good? They can pass straight through in a straight line through the atmosphere. They're not reflected or absorbed or refracted. Microwaves for cooking, well, it's absorbed by water molecules, these wavelengths, so it makes them vibrate, heating them up. Infrared cameras, all objects give out infrared, so the hotter the object, the more it gives out. So that's a useful application of that. Infrared cooking, well, we can use a toaster to grill our toast because infrared causes objects to heat up. We can use infrared for heaters because infrared causes objects to heat up. We can use visible light in fibre optics, so fibre optic broadband is getting more popular. Light reflects off the walls of the glass fibres until it reaches the end. So you could have a little thin piece of glass and our light will just bounce around on the inside there, and reflect around on the inside there. So UV tanning and sun tanning, UV light in sun tanning, why can we use this? Well, literally because UV tans the skin. UV light in security ink, well, UV hits fluorescent ink, which you can't normally see. It's absorbed and it's emitted as visible light, so it kind of makes it glow. We use UV in fluorescent lights because there's UV that hits a fluorescent material on the inside of the bulb, gets absorbed, and then emitted as visible light. X-rays in imaging, well, X-rays pass through flesh but not bone. They're absorbed by bone or metal, so they turn a white detector plate, they turn it black the more rays hit it. So that's why your bone in the middle of an X-ray will appear white, while everything else will appear black, and that's supposed to be a bone on an X-ray. I clearly can't draw those. And gamma rays and X-rays for cancer treatment, well, why? Because they kill all cells. Gamma rays are also used as medical tracers. So a medical tracer is where you might swallow a meal which contains radioactive materials, and this is because it passes through the body, it will pass out of the body easily to be detected. So a little bit on lenses then. So this here is a convex lens. When I shine parallel rays of light at it, they're going to converge. So we call it a converging lens or a convex lens. They're going to converge and they're going to go through a focal point F. Concave lenses, cave because of the inward shape of that lens there. This is a diverging lens, diverging meaning that they're going to split apart. Now we can find the focal point here by drawing imaginary lines backwards, and where they cross now, that will be the focal point. Magnification of an object is the image height over the object height. So if we find that the image is smaller than the object, we should have a number which is less than 1. If we find that the image is bigger, which is most things make images bigger, we're going to find that the magnification is greater than 1, so telescope or microscope. Now when we draw our ray diagrams, there are some golden rules here which are going to make this much easier to be able to draw. So the golden rules are: draw a ray undeflected through the straight through the lens. So here's our object. Here's a focal point on either side. Here's my convex lens. So convex is that shape. I'm expecting it to make the rays come together, okay, from the previous slide. So draw one ray straight through the middle of the lens. The next one goes parallel to the axis and then bends at the lens through the focus on this side. So parallel to the lens through the focus. Okay, should I need to, I can draw one on this side as well. So through this focus on this side, then parallel. And I'm going to see that my image is where the rays cross. Okay, so I'm going to keep the base of the object on the axis, and then I'm just going to draw the top of the object, just like the light comes from the top of the object here, that light is going to be at the top of the image there. Now I can say that this, I can say that this image here is inverted, upside down. He's a real image because I can project him on a screen, and he is diminished because he's smaller. So if he wasn't inverted, we would say he's upright. If he wasn't real, we would say virtual. And if he wasn't diminished, we would say magnified, meaning the opposite. Okay, sometimes if I bring an object inside the focal point, we get something a bit weird happens. So let's follow our same 3 golden rules. Ray straight through the middle of the lens. Okay, ray goes parallel to the axis and then through the focal point. Okay, well that's weird because I want my rays to be able to cross over somewhere, so what's going to happen here? Okay, well I can still make my ray go from the focus to the center of the lens and then go parallel, so still applying my 3rd ray, and you might think what a mess this is. Well, the magic here is that I can draw imaginary lines backwards to the point where they'll meet up again. So you can see these are spreading apart. I've got to draw rays going backwards. And when I draw those rays go backwards, they cross at the same point, thankfully, telling me that my image is going to be over here. So what can we say about the image this time? We can say that the image is upright. We can say it's a virtual image because I can't project it on a screen. And we can say that it is magnified because it's much bigger than my object. So this could be, for example, a magnifying glass. Okay, black body radiation. So we've already seen in our Leslie cube that dull black is the best emitter and that shiny silver is the worst emitter. Well, black body radiation, the perfectly black objects, are also the best absorbers as well as the best emitters. So the colour black is not only the best absorber of heat radiation, but also of all electromagnetic radiation. A black body would absorb all the EM radiation that hits it. They would also be the perfect emitters of radiation as well. So it won't reflect or transmit anything. Now, actually, a perfect black body doesn't really exist, but it helps us to understand some important physics ideas. So it's the perfect absorber and emitter. Now, a black body would absorb all the EM radiation that hits it and be the perfect emitter. It won't reflect or transmit anything. Now, let's have a look at these three stars here. We've got a red star, a yellow star, and a blue star, all at different temperatures. Our red star is the coolest, 4,000 Kelvin, and our blue star is the hottest there. Ignore the Kelvin, it could be Celsius equally. So we can see that the blue star is the hottest, and we can see the red star is the coolest. Let's have a look at these different wavelengths of EM waves that they're giving out. And here we've got intensity, basically meaning brightness. So what can we see here? Well, hot objects emit infrared, but they don't just emit infrared, because actually infrared is around here. So they emit a range of wavelengths around infrared. Now, the amount and type emitted depends on its temperature. So exactly which wavelengths are shown, as in what the distribution of wavelengths are, changes depending on how hot it is. Now, what do you really need to know? You need to know that as objects get hotter, the intensity of the peak increases. As in, when objects go from cool to hot, the peak intensity goes up. And you also need to know that the wavelength of that peak decreases. So here's the peak wavelength when it's cool. Here's the peak wavelength when it's warmer, and here's the peak wavelength when it's at its hottest. So the wavelength of the peak goes down, the intensity of the peak goes up. Okay, sound and ultrasound. So ultrasound is any sound or vibration above human hearing or above 20,000 hertz. You can answer either one of those will get you the mark for what is it. Ultra kind of giving you the clue there that it's ultra meaning like above. How does imaging with ultrasound work? So if we want to be able to take a picture of a fetus inside a womb, so what happens there is you get a partial reflection at each interface. So every time there is a boundary between a different material, you get a partial reflection as shown here. A little bit gets reflected, a little bit passes through. Now the reflected pulse is detected. So this reflection is detected here, and the time delay between the layers is used to indicate the distance between the layers. So for example, on a oscilloscope, you could see maybe the peak where the skin is reflecting, where the bone is reflecting, and then the back of the bone. We can use the time delay. As long as we know the speed of the waves through that, we can work out the distance between the layers, and that can build up a lovely picture for us. So we get fuzzy images, but they're really safe. And if you think about comparing it to X-rays, that's going to be really important with fetuses. Okay, question about lenses therefore. Is the principal focus the same as the focal point? Yep, the principal focus is exactly the same as the focal point, and the focal length is just the distance from the center of the lens to the focal point, or the principal focus. So focal length, distance from the lens to the focus, and the principal focus is exactly the same as the focal point. So a couple of uses of our ultrasounds here. Well, it's used for destroying kidney stones, literally because it just vibrates the kidney stones to pieces. Cleaning watches, so antique watches maybe. Detecting flaws in materials, cracks in building materials, so steel girders used for large buildings, things like that.
So further to ultrasound waves being used to study the structure of objects, seismic waves are studied to investigate the structure of the Earth. And earthquakes are the things that produce seismic waves, and seismometers are placed all around the Earth to detect these waves. And there are two seismic waves. There are P waves, which are longitudinal waves, and there are S waves, which are transverse waves. P waves are longitudinal. They travel through solids and liquids, and they travel faster than S waves. And S waves are transverse. They can't travel through liquids or gases, and they travel much slower than S waves. So the properties of these have helped us investigate the structure of the Earth. So let's say, for example, that an earthquake happened at this point here on Earth, if we're using this as our Earth model. The S waves would be shown to travel through the mantle of the Earth, both sides like this as the waves are generated, and seismometers around the Earth, for example here and here and here, would detect these S waves. But because S waves can't travel through liquid, then they can't travel through this liquid layer here, the outer core, and therefore you won't detect S waves around this area of the Earth if this was the original place of the earthquake. So they were looking at these S waves, and from that they surmised that there must be a layer of the Earth that is liquid, and this is the outer core. So that would be the pattern of the S waves, and the P waves, also generated by the earthquake, would also travel through the mantle, because they can travel through, well, the mantle's nearly solid, very nearly solid, slight movement on it, but they can travel through the mantle, and they also can travel through the liquid outer core. So you will see the waves going into this ring here, but they will refract when they get into that inner liquid ring. So they won't go in a straight line, you'll see them refracting and bending as they come down. They can also travel through the solid inner core, and then again through the liquid outer core, and again back into the mantle. And as they go through different mediums, they'll be refracting as they're changing speed. So with these S waves, there will be a small, with these P waves, there will be a smaller region on the Earth where seismometers would not detect any activity, so there'd be nothing detected in this region, but it can travel through the liquid outer core as well as the solid inner core. And these patterns of S waves and P waves help them understand which parts of the Earth structure are liquid and which are solid. And studying these waves helped to the current understanding of the structure of the Earth, where the inner core is solid with a liquid outer core, a mantle which is mostly solid with some slight movement, and then the crust around the outside. So remembering that S waves are transverse, P waves are longitudinal, and it is the S waves that can't travel through liquids, and that helped them understand which parts of the inside of the Earth were liquid, which were solid, and also the refraction, the changing of speeds as the waves go through, helped them again understand which parts were liquid and which parts were solid by looking at where the seismometers detected those P waves.
Okay, visible light and colour. So white light is made of three primary colours, red, blue and green. Now red paint absorbs all colours apart from red, which it reflects. Green paint absorbs all colours except green, and so on. Now, the only things you might want to know there is that black paint absorbs all light, and white paint reflects. Sorry, let me put that around the right way. Black paint absorbs all light, reflecting none. White paint reflects all light, absorbing none. Now, filters work by only letting the colour through that is the colour of the filter. So all of the other colours are absorbed apart from red light. Now, if we have a look at a blue dress is absorbing all of the wavelengths apart from blue. Excuse me. So green light and red light are being absorbed by the dress. It's only reflecting blue light. But if I was to put a red filter over this, because a red filter only lets red light through it, and there is no red light coming off of the dress would look black. Okay, electric motors and loudspeakers. So all of this kind of topic of the electromagnetism all really have similar kind of science behind them, underpinning them. So how a speaker works then? Let's have a quick look at our diagram here. What have we got? Okay, we've got a speaker cone. That's the kind of cone-shaped thing you might see on the front of a speaker. Behind the cone, so when we look at the front of a speaker, it might look like so. Well, there's our cone here from the front. Normally you might have another little one at the top there. So this is our cone that we see on the front of the speaker. Inside we've got this cone is attached to a coil of wire, just here. And this coil of wire is inside this kind of magnet. So there's a north and a south shape of the magnet. Now from above, the magnet looks like this. I've got a north in the middle. I've got a groove in it where my coil sits, and then this circular bit around the outside is the south pole all the way around. So my coil sits, as I'm looking at it from above, sits in there like that. Now from the side he looks like this. So we've got an input voltage where I'm putting in some electricity into my coil of wire. Now let's think about what happens when I put electricity through a coil of wire. It becomes an electromagnet, having a magnetic field around it. So let's see how this works. AC current is sent to the coil, my coil of wire, which is attached to my paper cone. The coil is inside a strong magnetic field of the magnet. When current is flowing, it generates a magnetic field around the coil, just like an electromagnet. This interacts with the magnetic field from the magnet, and it generates a force which moves the cone. As the current alternates backwards and forwards, it moves the cone backwards and forwards, creating areas of compression and rare refraction, which are sound waves. So cone moves in and out. As it moves in and out, it compresses and rarefies the air in front of it. The frequency of the sound waves are the same as the frequency of the AC current. Okay, generator effect then. So this time, instead of using electricity to make kinetic energy, as in a motor, we can reverse this process and we can turn the movement into electricity. So here we have a magnet, and that magnet is being moved into and out of a coil of wire. Now, the generator effect is the induction of a potential difference across a conductor, the conductor being the coil of wire. Induction, meaning to induce, meaning to create, the creation of a potential difference across a conductor. Now, if I connect it in a complete circuit, current can flow. So when the conductor, and this is when the conductor experiences a changing magnetic field. So I'll say this again, the generator effect is when I induce a potential difference in a conductor, when that conductor is experiencing a changing magnetic field. So how do I produce a changing magnetic field? I literally either move the coil in and move the magnet in and out, or I move the coil in and out. So what factors can affect the size of an induced current? So the current that I might feel here on my ammeter would be the speed of the movement, so how fast I move that in and out. What affects the direction of the induced current? Well, the direction of the movement of the magnet or coil. So as I move it in, the current will flow one way. As I pull it out, the current will flow the other way. Now, if I swap the magnet round, swap the poles around, that will also change the direction of the current. Now, when a current is induced in a conductor, the induced magnetic field opposes the original change. So what I mean by that is if I move a south pole, into a coil, like here, the induced current in the coil creates a magnetic field in it that opposes the change that I'm trying to do. So if I'm pushing a south pole in, it's going to want to oppose that. So how to oppose a south pole going in is to create a south pole here, which pushes against it because they repel. If I was to pull the south pole out, it's going to want to oppose that. So it creates a north pole there to attract the magnet back in again. Now, applications of the generator effect. So here we have the standard generator. It's what's used in power stations and wind turbines, and it produces AC electricity. So it looks really similar to a motor, but this time instead of me putting in kinetic energy and getting out electricity, sorry, let me try that again. This looks like the electric motor, but instead of putting in electricity and getting out kinetic energy, I am putting in kinetic energy and getting out electricity. Now, the standard generator, the alternator, produces AC current. It just has slip rings and brushes. It doesn't have the split ring commutator. So this is going to, as the coil is rotated by whatever's powering it, steam turbine, steam passing through the blades of a turbine, or a wind turbine, this coil is going to cut through the magnetic field lines of the magnet, and it's going to induce a voltage in that coil. As one side of the coil moves upwards, the current will flow, and as it spins down, that same side moves down through the field lines, the current will flow in the opposite direction. So as it spins round, it's going to make the current go forwards and backwards as it spins round. So this is going to give us the output of AC current, where my voltage alternates in the plus and the minus direction, forwards and backwards each second. Applications of the generator effect, so the dynamo, this could be used in batteryless bicycle lights and wind-up torches. It produces DC. The reason why it produces DC is because we've got one of these split ring commutators here. So it's got a split ring commutator, so the connection swaps every time, and this keeps the current flowing in the same direction each time. So this produces DC current. Okay, so applications of a generator effect, the dynamo, because of its split ring commutator, the current's only going to be flowing forwards. Now, of course, we don't get any voltage induced at the point where the motor, the loop of the motor, needs to cut through field lines. And of course, if these field lines are going horizontal here, when the wire is sat upright, so it's at the top here, that wire is not cutting through any of the field lines as it goes along the top, at the very top where it's going horizontal. It's only where it cuts through field lines that it induces voltage. So microphones, really it's the same story as speakers, just in reverse. So instead of having an AC input and it producing kinetic energy as the sound wave, making the cone move, this time it's going to be sound waves that make the cone move, that ends up giving out an electrical signal. So sound hits the thin cone, making it vibrate. So those areas of compression and rarefaction in the sound wave. The cone is connected to a coil of wire, so just a normal copper wire. That is inside a magnet, so in a magnetic field. So the cone moves the coil of wire when sound waves hit it. The moving coil cuts through the field lines of the magnet. This induces an alternating current in the coil, which has the same frequency as the sound wave. So the frequency that's in the electrical signal that comes out will be the same as the frequency of the sound waves that go in. So transformers. So from our P1 paper, we know that that is the national grid. And the national grid, the purpose of it is to transmit electricity around the country. It does that in an energy efficient way by stepping up the voltage to reduce energy loss through heating, and it steps down the voltage to make it safe for consumers to use. Well, we need to be able to do some calculations now. Now, if we look at the transformer in a bit more detail, we've got a primary side. That really just means an input side where if it's here next to the power station, this will be the where the electricity from the power station comes, and this is it being sent to the cables. So on this side, we can see we've got lots and lots of coils here. On this side, we can see we've got fewer coils. Now, the ratio of the number of coils on both sides is the same as the ratio of the voltages. So this gives us our equation of the voltage in the secondary over the voltage in the primary. So our ratio of voltages is the same as the ratio of the number of turns. This equation is lovely because we can swap it round if we need to. So you can literally just flip it and it's still correct. So Vp over Vs equals Np over Ns. S and P just meaning primary and secondary. V and N just meaning number of turns and voltage, We can flip it around, and that can make the mass handling just a little bit easier. Now, we pretty much say that these are nearly 100% efficient. They're not really, but we do like to say, to make the calculations a bit easier, we can say that the power in equals the power out, because that means that we can do P equals IV. Because P equals IV, I can say that the current times the voltage on the input side, on the primary side, is the same as the current times the voltage on the secondary side. Now, really, they're not 100% efficient. Actually, there'll be a little bit of warmth. It'll make the transformer warm up a bit and make it waste a little bit of energy. Now, a couple of notes about what this is made of. This is made of iron, this square here. It's not made of copper. It doesn't transmit any electricity. It's made of iron because it can just funnel the magnetic field lines through there. And we want the field lines to be felt across both sides because of our explanation of how this works. So here's a close-up of our transformer. Apologies for the fuzzy image. So AC current goes into the primary coil. It has to be AC because we need it to be a changing current. Now, the primary coil produces a constantly changing magnetic field. Because the current is flipping directions, the magnetic field will flip directions. So there will be a magnetic field around this, which is flipping backwards and forwards, backwards and forwards. Now, this magnetic field is felt by the secondary coil. You don't need to say much more than that. It's felt by the secondary coil over here. This induces an alternating voltage in it. This is called electromagnetic induction. And the secondary coil experiences the same frequency of voltage as the AC in the primary. So let's just go through that again. The primary coil creates a changing magnetic field around it because of AC current. That's felt by the secondary coil. It's called electromagnetic induction. And the secondary coil has the same voltage as the same frequency of voltage as the input voltage on the primary coil. Okay, onto something slightly maybe more fun than transformers. The space topic. So in our solar system, we've got one star, the sun, plus our 8 planets and the dwarf planets that orbit around the sun. We've got natural satellites as well. So there are moons that orbit planets. They're also part of our solar system. And our solar system is part of the Milky Way galaxy. And our sun was formed from a cloud of dust and gas called a nebula, pulled together by gravitational attraction. It's gravity that made them all stick together. So this is about the life cycle of stars. People revising today seem to really know this. All stars start out as protostars. Dust and gas falls into the protostar due to gravity. That falling gas and dust heats up. When it gets really hot, fusion starts. And when fusion starts, the sun comes to life. The star comes to life, and we call it a main sequence star. So fusion has started at this point. And we can see there are going to be 3 pathways through this life cycle of stars. You need to know each of the 3 pathways. So for the smallest mass stars, they use up all their fuel as a main sequence star. They expand because there is a larger outward force of pressure of fusion. The inward force of the weight of the star stays the same. Once they've used up the last of their fuel as a red giant, they're going to cool down into a white dwarf. And they'll cool down even more into a black dwarf, and they'll just stay there like that. So that's the smallest mass stars. Now, heaviest mass stars, they go from being a main sequence star, and because they're heavier, we call them a red supergiant. Now, these ones, once they've used up the last of their fuel, they're going to rapidly contract inwards as they use the last of their fuel. The outward force of fusion really drops dramatically, meaning they collapse inwards. And as they collapse inwards, this is now during a supernova, as they collapse inwards, there is an increase in temperature which does the last little bit of fusion. And this last little bit of fusion is really important because in this last little bit of fusion, it's so dramatic, so much energy is released that the star explodes in one of the largest events that happens in our universe, an exploding star. And during this supernova, elements which are higher than iron in the periodic table, heavier than iron in the periodic table, are made. Up until this point in the red supergiant, up until the supernova, fusion is fusing together all the small nuclei into larger nuclei and working its way up through the periodic table. So all of the elements which are found on our planet are because our planet is made from the dead remains of old exploded stars, which includes old supernovas. And we know that because we have elements heavier than iron on our planet. Now, after a supernova, you're going to end up with something left behind called a neutron star, literally just made of pure neutrons. And these are very, very dense. And our medium-sized stars will end as that. Now, the very heaviest mass of stars will end up going from a neutron star straight into a black hole. So it collapses under its own mass, and it has no volume, and it's so dense, it's got such high gravity that light itself can't escape from it. So we call it a black hole because light can't escape from it, you can't see it. Okay, orbital motion. So velocity is speed and direction. It is a vector quantity. And when in circular motion, the velocity is constantly changing, but not the speed. So it's accelerating, because acceleration is a changing velocity. So we can see our object going around here. If we were to cut this string at any point, the object would just fly off at a tangent to the circle. So an example of uniform circular motion, a planet, the moon around the Earth, fairground rides. So if a planet or a moon is in a stable orbit, meaning its height isn't changing, if the speed changes, the orbit radius has to change too. So to make things spin closer to the center, we need a faster speed. So Mercury orbits very quickly, and if we have a larger radius, we need a slower speed because this is because the force of gravity is stronger the closer to the object you are. So redshift then. Redshift is a really great piece of science, a recent discovery that's proved so much about what our universe is and how to explain it. So if we have a look at objects moving towards us or away from us, so when an object is moving, let's say we are this eye here, when an object moves towards us, the waves that are given out to it become compressed, because as the object moves, each is moving towards the wavefront it's just given out. So if it's giving out the same frequency of waves and it's moving towards you, the waves appear squidged up. And similarly, if I have an eye that's over here looking at this light over here and the object is moving away from me, well, each time it gives out that same frequency of wave, the waves are going to be spread out. So light waves are stretched, showing redshift, and light waves can be squashed, showing something called blue shift. Now, when we look up at our star, we see the rainbow of colors from it, and we see that there are little black strips on the rainbow of colors from our star. Each black strip is due to the atoms that are in the sun. So those atoms absorb specific frequencies of light, and we can show this in a lab. So we call these absorption lines. Now, when the Earth is looking at a star which is the same distance from us, like our sun, we can see where those absorption lines are. Now, when the sun, another star can be seen to be moving away from us, well, those absorption lines just shift a little bit. They shift over, and they shift towards the red end because the light waves are stretched, and red light is slightly longer wavelength than blue light. So when objects move away from us, their wavelength becomes stretched, and the absorption lines move towards the red end of the spectrum. So this is evidence for, we'll explain why in a second, this is evidence for the universe expanding. How does it prove this? So light from distant galaxies is more red than expected. The majority of distant galaxies are much redder than expected. The absorption lines in the light are shifted towards the red end of the spectrum. The further the galaxy is away from us, the more red-shifted it is, and so the faster it is moving away from us. Now this means that all of space is expanding. And I saw a model for this. So when you make a kind of bread with currents in it, and you first put it into the oven, it hasn't risen. And so the currents are all quite close to each other. And then the bread will have risen after a little while in the oven. And each of those currents will now, when they look at each other, let's say this red current in the middle, this current in the middle looking at the others, all of the other currents will appear to have moved away from it. Okay, no matter which direction it looks, every current has moved away from it. And that is because literally the bread has expanded, and we're seeing the same thing in our universe. If we rewind all of the positions of the galaxies right now, rewind them all to when they started off in the same place, well, this proves the Big Bang Theory. Okay, so just over 13 billion years ago, we can find the exact date of the Big Bang, because when we rewind the position of all of the stars in the galaxies in the universe, we rewind where the positions would be. They all joined together in one spot just over 13 billion years ago.